Hi everybody, Mr. Neff here. Let's talk Newton's synthesis of Kepler's third law. So about 50 years after Kepler put together the law of periods, remember that's the one that has the period of 1 over period of 2 quantity squared equals the radius of 1 over the radius of 2 quantity cubed. About 50 years after that, Newton showed that you could do this with just knowing the mass of the thing that you're orbiting and the universal gravitational constant. Now, ironically, Newton never knew the universal gravitational constant, and so he knew that you could do this, but he still wouldn't have been able to do it until Cavendish came along in 1798. Still, let's talk about what Newton did here. So Newton said, okay, you got something like the sun, and you have something like the Earth, and it's orbiting. Now, he said that that's forced motion. That's only going to happen if you have a net force on it causing the centripetal acceleration. So Newton said that your centripetal force is equal to the force of gravity. All centripetal forces are the mass of the thing that's doing the circle times the centripetal acceleration, or in this case, tangential velocity squared divided by the radius. Now, the force of gravity of between any two things is going to be the universal gravitational constant, big G, times the mass of the two things in an interaction. Here I have the Earth and the Sun, and divided by the radius between their centers squared. Now, I can cancel out the mass of the Earth, which is funny. That means that this doesn't actually depend on how big the Earth is. I can also cancel out one of those two radii, and I can take a square root. And I get this interesting thing. This is the velocity that you must have to orbit at this distance. And so we would call this the orbital velocity. And it's interesting because at a certain distance, there is only one velocity that will work. And so if you have something like the Earth and you want to try to send up a satellite and get that thing to orbit, well, you have to give it tangential velocity. And if it's too fast, that thing will not be able to orbit. If it's too slow, that thing won't be able to orbit. If it's too fast, there won't be enough centripetal force to keep it in a circle, and you'll lose it. And if it's too slow, there'll be too much centripetal force, and it'll crash into the Earth. And so there's only one velocity that's going to work for a given radius. So that's an interesting thing. But he goes on with it because that's good, but that's not what Kepler was showing. Kepler wanted to have period in there. So Newton said, okay, well, for anything that's going in a circle, the velocity is 2 pi r divided by the period. That's just distance divided by time. And so now you can see what we're doing here. We'll square both sides, make that numerator 4 pi squared and r squared over period squared, and now this radical goes away on the right side. Now I've got 2 r's and another r down in that denominator, so I'm going to make it r cubed with the 4 pi squared, and then that's going to be divided by big G and the mass of it's the sun here, but it's really whatever you're orbiting. And that's going to be equal to the period squared. So this looks a lot like what Kepler said. It's a relationship between the period squared and the radius cubed. But notice that it only has the data for one object in it, the period and the radius for one object, and then it has this sort of complicated constant of proportionality. Sometimes they call that K, which does make some sense. It is a constant for a system. So there's going to be a K for our solar system. Why? Because all the things orbit the same center. There's going to be a K for our Earth system. Why? Because all the satellites in the moon orbit the same object. And so all that to say, there's a K for the system. And then each item that's orbiting, well, there'll be a particular period for a particular radius. And so the period and the radius combination will be unique, and they're both directly proportional to each other, not in a linear way, but still the bigger the radius, the bigger the period is going to be. And so you have something like the sun, and then the planets go out from there. Well, the farther out you are, the longer and longer it's going to take for the one orbit to happen. one quick example of that to show you how you could use this. Here we have a moon of Saturn. Now you know on Saturn there are many moons, but here's a particular moon of Saturn, and we know its radius and we know the period that it has. They want us to use Newton's version of Kepler's third law to find the mass of Saturn. So what I can do here is I can say, all right, well, Newton's synthesis of Kepler's third law is period squared, radius cubed, and then the constant of proportionality is this K value. And this, I had ms before for mass of Sun. This time it means mass of Saturn. It's whatever your orbit. And so now all a person would have to do is put in for the period 23 hours, but because remember the unit on big G is 6.67 10 to the minus 11 Newton meters square per kilogram squared. Inside of that, Newton, remember, that is a kilogram meter per second squared. So I need to have the left side of this equation in seconds. It's the only time unit in this whole thing. So that's going to be 23 times 60 times 60, and that will be in seconds. That's going to get squared. I did that before I started the video. 82,800 seconds is what is going to be squared there. And then that's going to be equal to all of these things. I'll take this 1.87 times 10 to the 8th meters, and I'll plug it in there. Don't forget to cube it. And after you put in everything that you know, the only thing there that you won't know is that mass of Saturn. And if you're careful on how you get that into your calculator, you will end up with 5.6 times 10 to the 26th kilograms. And you can fact check that. That is what the mass of Saturn is.